So after performing logic synthesis, the logic synthesis tool reported that there is a need of 3600 ALMs and close to 7000 ALETs. And the logic synthesis also reported that there will be requirement of 7000 ALETs instead of cyber workbenches 41,000. So after performing logical synthesis, I extracted this RTL code, brought it to Questa. So after performing logic synthesis, I brought the RTL to Quartus to perform RTL simulation. So this is the RTL code generated by Cyber Workbench. So for this, I wrote a test bench to test the RTL in 14 different test cases. So of this, 6 test cases are AES-128 protocols documented test cases, and for the remaining, I had run the application manually using the software and extracted the expected cipher. So by this, it will first send the key, plain text, and it will read back the encrypted data and compare it to the expected value. So I'm gonna run the simulation using Questa. Run simulation. Simulation run all. As you can see here from the validation summary, so there were 14 test cases and all 14 test cases have matched the result. So after completing this, I proceeded forward with the FPGA implementation of the project requirement, that is configuring it with SoC system to make sure that it communicates properly with the HPS. So for that, I used the golden project provided by TerASIC, where they had incorporated AXI Lite into the project itself. So here for my requirement, for the AES-128 encryption to perform on the hardware, I need two 128-bit inputs from HPS and one 128-bit output towards the HPS. So in order to accommodate this on AXI Lite, so I used multiple PIOs because each PIO is limited to 32 bits. So for each input and each output, I've split it into 4 blocks before sending the data. As you can see here, I have 4 PIOs just for key and 4 PIOs for plain text and 4 PIOs for ciphertext. All of these are address mapped to their unique addresses, which will be updated in the header file so that the HPS can read and write to these addresses. So on the top module for this project, I've incorporated these PIO pins for the system SoC so that they can be used in the communication and I've also instantiated my top module. Here, since the RTL generated the key was mapped as a array, memory mapped array, so I had to send in data by mapping that to a memory, which again is being done here. So 3 into the 32-bit key value is being converted into 6 cross 18 8-bit key memory. So by doing this, I'll be able to send it to my encryption module. So the results generated by the encryption module is again returned back to the HPS using the Axelite bus. On the HPS end, I've implemented all the required steps of sending data to the FPGA, reading back the data from the FPGA, then performing software decryption, software encryption, and then comparing all the results. So as you can see here, the code generates random key, reads input from the user, that is 16 ASCII characters, sends it to the FPGA by performing memory mapping. Here it is doing the memory mapping, and then here it sends it to the FPGA and waits for the FPGA to calculate the results, and then it reads from the memory for the cipher data. So once that is done, it performs software encryption of the plain text, software decryption of hardware cipher, and then software decryption of software cipher. Once that is all done, it performs the comparison and provides us the comparison result. Yes.
Hi there everyone. I'm going to be continuing from where my classmate finished his explanation. Here I'm going to dump our RTL bit stream into our FPGA. And now let us take a look at our putty. Here you can see that we already have our device mounted and ready to run. So now let us go through all the steps of the code to make sure that we are not missing out on any steps. Here, as you can observe, that we have given the input as this, and it is a 15-digit input, and our FPGA program has compensated for it by adding a 00 at the beginning of our input plain text. The FPGA has successfully communicated this onto its memory, and it has been sent. It is done encrypting and reading the ciphertext and completing the software encryption. Here we can observe this is the encryption key, and here we have our plain text, and this is our plain text in its hex format. Here let us take a look at the encryption results. This is the ciphertext we have received from our FPGA. As we can observe, the ciphertext from the FPGA and the ciphertext generated from our HPS software program are the same. Now let us take a look at our decryption results. Here we can observe from our hardware decryption, the plain text from the FPGA is the same as the plain text we have inputted, and the software decryption also gives us the same plain text. This proves that we have provided a successful AES encryption and decryption from the hardware and software. Thank you so much. It was success. Thank you. Goodbye. Thank you, FPGA course. We will see you next time.